All right, so far Bila and Brian not yet here for the record of this video recording. All right, as you can see on my screen, can everyone hear me, right? Okay. All right. Now, if you're not able to see anything from my computer or anything go blank in your screen, just let me know. And also, if you're not able to hear me, just let me know. Or you can go to the text there and communicate. All right. Now, just to recap, what we have covered last week is that we're looking at a moving non-deforming control volume with we focus mainly on the velocity vector, and because of the moving control volume, we can derive or we can split our vector into two additional vector, which is here on the screen. Here you see your V can consist of W with this relative velocity and also control volume velocity right here. So, and then last week we looked at example of our engine machine, our aircraft machine, right? Right, today we look at another application of this vector equation, right? Which is your tutorial question 12, question 12. So we look at an application on a sprinkler head. I think this one will come out, this kind of question come out in one of the final year question. I think a few years back, right? So, yeah. So given a water enter a rotating sprinkler through the base here, at a steady rate, given a certain number of the rate, acid area was given also, and however be careful because the area unit is mm square, so be careful on the unit because we need to always change it to a unit SI in your calculation. Yeah? So we need to find three things. We need to determine average speed leaving the nozzle, which is here, all right, relative to the nozzle if there are three settings here. The first case we look at average velocity, speed when the sprinkler head is stationary. Means we lock this sprinkler head, means it do not move. We just look at what happens if you lock this sprinkler head and then water input from bottom go up and then come up from two head here. So what is the velocity here? Right, you're given area section 2 here, and then area section 1 not given, so we need to find later on. Right, so again these are all the parameter we have. Steady rate, the word steady rate of 1000 ml per second, and acid area of two nozzle here and here, same 30 mm square. We need to find the average speed. All right, now we look at the first case when the head is not moving, means the water just follow the control volume and then come out. Right, we start with the conservation of mass equation. So I think this is I think lots of time we see this equation. So call out the continuity equation, consists of your control volume and control surface. Again, because it's a steady, so cancel the first term equals 0 and write the steady. So by writing this one in your answer, you'll get some marks for this one. Usually it's 1 mark for this small note here. Just cancel, and just to show us that you understand what happened when you have a steady flow, what happened to the continuity equation. So this is also one of the learning outcome, one of the expectation from you. All right. Now, after you write out the continuity equation simplify the equation because of the flow condition. In this case, we have a steady flow. So we only have a control surface condition. And remember that we have an inlet and outlet. So be careful, whatever is in is negative, whatever is out is positive for control surface here. All right. So again, this term here is your m dot. The whole thing, the second term in the continuity equation is m dot. M dot equal to rho AV. And again, because we have a moving control surface here, moving control volume here. So our V here, in the earlier example, we are using V, but however, because our float is changing their area here, right, from bottom to the head. From here, you see that the volume is changing. So your velocity is changing. So we need to use the W, right? Relative velocity, W, right? Yeah. So again, in the exam, if you write the wrong denotation, also you get the wrong marks, right? So you need to be careful when you apply the equation, right? So again, by looking at this equation, we have in and out here. So we have one point here, section 1, right? 2 and 3, right? So we have 3 points we're going to focus. The first one is here, section 1, section 2, and section 3. So we know that section 1 is going in. Section 1 is in, section 2 is out. Section 3 also out. So negative, out is positive. And for this term, this equation here is m dot. M dot equal to rho AV. Of course, this case, your V replaced by W. Huh? Right. So you just put in the small denotation just to mark that the location of the interest. So means we focus, if you write 1 means we focus on 1, you write 2 means focus on 2, 3, and so on. Huh? So negative because it's in, positive because of out. So before we move to the next slide, any question on the site we use or anything that you don't understand?
Good, sir. Okay.
Okay, good. All right, let me know if you lost or you're not able to understand the way we solve. Okay, so water in this case we consider as an incompressible flow. Water in this case we consider incompressible flow. So in your answer there, you can write your assumption. So assume your water is incompressible. So once it become incompressible, your rho is the same inside the equation here. All right. So you can cancel out. You can factor out and then you can cancel, or you can straight away take away your rho here. So we simplified further this equation, become negative AW section 1 plus AW section 2 plus AW section 3. Yeah. All right.
How can we find the density is the same?
You mean density? In this case, you don't need to use a density because your water is incompressible. So when it's compressible, all the density here is equal. So you just take out from this equation.
So the continuity equation. So for in this case, we are using a W, right, for
Yes,
replace
correct.
P.
Yes, correct.
We are using the W for the
In
moving
this case,
object.
yes, because our our control surface here, like the previous slide I showed you, because we are looking at moving non-deforming control volume. Right, we're looking at moving control volume. All right. Yep. Okay. Do I answer your question just now on your density?
Yeah, I got it.
Okay, good. All right, we continue with the steps. So I think you understand why we have a negative AW plus AW section 2 plus AW section 3. So, and then we know that AV is your Q with your volume flow rate. All right. So a few understanding is that all these are Q. This one is Q1, Q2, Q3. In this case, 2 and 3, the area is the same. All right. And your W, because it's the same area, so your velocity come out from section 2 and 3 will be the same. So these two will be the same magnitude. All right. So we can simplify further this equation, because this equation you have 6 unknown there. 1, 2, 3, 4, 5, 6. 6 unknown, you simplify, become 3 unknown. Become 4 unknown. All right, and then you further reduce it. All right. So from this step to these steps, we simplify because of the area and the velocity come out from the section 2 and 3. Relative velocity come out from the 2 and 3. So we have this equation. Again, be careful to carry forward your negative sign when you write your answer. All right. I've seen some students when they do the answer, they know how to do, but when they carry forward the answer, they forget to carry the sign sometimes. So when at the end, they will get some very weird answer, right? Then you rearrange, because we're interested to find the velocity come up from the head here, right? So W square, W2 equal Q divided by 2A section 2. And I think all these parameter was given in the statement. All right. So in the statement, if you read the statement, the rate of 1,000 meter per second, 1,000 ml per second, and also the nozzle size was given. However, in this case, the nozzle size is mm. So you need to do the conversion into unit SI into this equation. All right. So in this case, I will skip all the calculation, all the detailed calculation. So you will get W2 equal to 16.7 meter per second. All right. So we get the first case scenario settled for first set scenario when the sprinkler head is not moving or stationary. Now we look at section B. What happens when the sprinkler head rotates at a certain speed, round per minute, RPM, round per minute, or revolution per minute? All right. All right. Now just a bit statement here. So W2 is independent of the speed rotation of the sprinkler head and represent the average velocity of the water exiting from each nozzle with respect to the nozzle for the case A, B, and C. Right. So in this case, no matter whether the sprinkler head rotate or not rotate, actually the W component, the relative velocity come out from the nozzle head is actually the same, like what we found in the section A. All right. However, if you want to find the V2, the absolute velocity, then it will be different. Because in this case, we are looking at W relative velocity. However, if the question changed to find velocity, then or V2 component, then it will be different. Okay, just notes for section B and C. If you only look at relative velocity W component, then it will be the same whether it's rotate or not rotate.
Sir, I don't understand it properly.
Okay, now W component is a relative to something, right? Relative to something. So you don't understand the W and V here, right? These two statements, right? So okay, now imagine you're standing here, and you look at how fast the water spray from here. You look from here, then you look at this point. So let's say you're sitting at here, you sit here, and then you look at this water spray out. So the first case is you do not rotate, means the water does spray out from here, and you find the value. In this case, we find 17.7 meter per second shoot up from this head, from this location. So the case B and C, this sprinkler head was rotate. Imagine you sitting here without moving, and the sprinkler head was moving. Actually, you are seeing the same thing, whether it's moving or not. Correct? You imagine you are sitting here, and then you look at here, and then suddenly the sprinkler head moving. Actually, what you see here is actually the same. It doesn't matter whether how fast this sprinkler head moving. However, if you sit at here, for example, and you look at this point, this is a first scenario. First scenario, we focus on W. This one, second scenario, you focus on V. So you look, if you sit at here or you stand at here, and you focus on this point. So when it's stationary, you look at this point. You will measure at 16.7 meter per second, let's say, and you turn on the sprinkler head. So this one will move to this side, and it will sprinkle this way, and then the head will become here, and it will sprinkle this way, for example, and so on. So when you look at this position to this point, this point, this point, the velocity will be different because of the rotational speed W here. I mean the RPM that you set here. The water will spray at different speed if you stand here, rather compared to you sit at the cap here. Do I explain? Do I make you a bit clearer of between these two?
Yes, sir. So for the B, it will be average velocity, and then for the C, it will be a specific velocity lah. B, correct?
No. Okay. Okay. So actually, it's just a trap question actually. So if you look at the statement, so what you need to find is the velocity speed from this head here. You want to find W2. So the first one, you follow the procedure, you get 16.7 meter per second. And then the second one, it asks you what happened if the head rotate. What happened to the W component again? All these are ask you about W. So what happened if the sprinkler head rotate or accelerate? So actually it's the same because you're sitting at this position and looking at this, because the distance here is same. You do not move from this location, you see. Yeah. So, and then only when it's different when it asks you to find V. What is the V if you refer to the bottom here or at this point or you stand here? Will it be different? Of course it will be different, right? Because of the reference axis that you choose, X, Y, Z that you choose. Okay. You look here to here will be different, and the sprinkler head from here to here will be different. If the sprinkler head like that, the water spray from here will be different if you look from here. Okay, and so on. So this is just to remind you that it will be different if you find different things. In this case, it asks you to find average water, which is from the W2, right? Relative here, the word give you a keyword relative to the nozzle. Okay. Or if you really want to look into more deeper, is that because this one it gives you relative to the nozzle, means you're sitting at this nozzle head here. You're sitting at this nozzle head here because it asks you, it say here relative to the nozzle. So this is a nozzle. So you sit here and look at the water. So no matter it's spin or not, it's still the same, right? Yeah. Okay. All right. Now there's a equation there, which is because you are given this equation in the earlier vector equation given in the tutorial question number 9, the diagram gives you this equation, V equal to W plus U, right? Or V equal to W plus the VCV. So in this case, your VCV is U. So U you calculate from the omega times R. All right. Omega is the angular velocity. Angular velocity usually is radian per second. Radius is from the distance, radius, right? So yeah. All right. Okay, we have done question 12. We go to question 13 now. So previously was still under non-deforming. Right. Previously is about non-deforming. Now we look at what happens if you have a deforming control volume. So deforming control volume, you know that when it's deformed, it will change volume and control surface also. All right. So be careful when the question mentioned that you involve a deforming control volume or your control volume is changing. So the Reynolds transport theorem that we use for moving control volume is given by this one. Just now we see already. So for moving control volume, we have this term, change of mass in the system, or m dot in the system, equal to what change in the control volume plus what change in the control surface. However, in this case, we are referring to W, which is relative velocity rather than the absolute velocity. So write this one in the question 14. All right. So in the previous one, because of the steady states, we cancel out for non-deforming. However, under deforming control volume, this one is not zero. this component is not 0 when it is a deforming control volume. Deforming means the control volume is changing already. So this one not volume.
That we never get 1 mark, sir.
It's not get 1, is that it's not equal to 0. You cannot cancel out already, even though you have a steady flow inside the system, because the control volume is changing. Okay, yeah, means your control volume is deforming. All right. Previous example we look at, for example, give you a cube like that. All right. So previous example, we always look at our float will come in with a steady, and the control volume, the space that we're looking at is do not change. But when your in this case is that when your control volume come in, because of the water pressure, it will expand. So your volume become bigger compared to the previous one. So this one is the deforming case. So when you're deforming case, your first term of your Reynolds transport theorem here cannot become 0 already. So just be careful on this one. All right. Yeah. And this one just notes, extra notes to remind you that velocity here we look at relative velocity. Velocity reference to the control surface. So this is again the side note for the velocity vector, right? Velocity vector. Let's see, CV. In this case, is a VCS here. All right. Previous one is VCS. Now is VCS because we have a changing of control surface. All right. So yeah, in this case, be careful on the vector equation. Right. So just make a side note on this equation. So our absolute velocity, VCV equal to W2 plus VCS. And VCS is a velocity of the control surface. And this one from the fixed observer. Anyway, you will see this, you understand more when you come to example later on. Okay, we look at one example. This is question 15. So you have a string here. So and this plunger have a face area of certain face area. In this case, be careful on the unit. Purposely put in mm². So liquid injected steadily into at the rate of cm³ per minute. Again, be careful, or minute. So, and we have a leakage. We have a leakage past the sponger is 10%, 10% of the volume. 0.1 times the volume flow rate out of the needle. So we need to find with what speed should the springer be advanced. So it means how fast that you should press this holder here, so that your eject rate here is 300 cm³ per minute. This is our main objective. For example, you are doing operation and you need to inject a certain morphine into the body. All right. So and there's a loss inside the leakage inside the apparatus. So you need to calculate what speed that you should press from the machine to give the patient a certain amount of medicine. Right. All right. So I want you to sketch out whatever you see on the screen here. So you just draw out the control volume. You can draw out the strange profile, right? So in exam, what we're looking at is the red color, the control volume here. So yeah, so when you draw, make sure your friend able to understand also. So when we check your answer, we know what you're talking about. So draw the strange, and then you don't need to draw so detailed. Just stretch out, and then you have the control volume, and input all the parameter there. So the first parameter is the length L that you should press, and then yeah, and then you have a area here. So you have an area of a plunger, which is the surface that push the liquid into the syringe here. So your area here is 500 mm square, and water come out from this area. Again, the area here is a little bit angled area. It's not the right angle. It's at a certain angle here. So you measured from the area here. So the area calculated is 300 cm cube per, no, the water come out from here is 300 cm cube per minute. So this is a Q. Area here is not given. All right, and then there's a leak there. Leak is 0.1 Q2, which is from here. Okay, and then label your control boundary, your boundary condition. You have section 1 and section 2. Yeah, so these are the standard format that we're looking for when you solve control volume question. So you drop out, and then we look at the control volume is first one, and then where is your section 1, where is your section 2, and then parameter given. Okay, we have a velocity of the plunger, VP. So we need to find our VP, this one, in this case. So how do we solve this question? Right, I will still put the diagram on the hand top corner of the monitor. So again, this is the deforming control volume, because our fluid from the plunger volume here or chamber here change into a very tiny control volume when it enter into our needle here. All right. So recall again, write out the Reynolds transport theorem for moving control volume. Again, remember on the W, if you write V here, means you give me the wrong Reynolds theorem. Be careful on the equation that you use. Even though it will be an open book and online, you can copy, so make sure you copy the correct one. Okay. All right. We look at the first one first. We look at the first one first. The first component. And equal to 0 means the continuity equation apply. Means so whatever come in will be same as out. All right. In this case, we consider the leak also. That's why our system can be 0. So this one we copy. Del over del T, integrate your control surface, control volume, rho dV volume, plus, and this one is your m dot again. So you have in and out. All right. So you have section, you have m2 out positive. All right. And then m dot leak equals 0. Here you can see there's no m dot in here. There's no negative input from here because we start with the constant volume here, and then we pump in, right? We do not inject any additional liquid into this device. So that's why we don't have something on the section 1 here, right? So, yep. Any question on this equation before we move on? Again, now we are looking at deforming control volume. It's a bit different from what we discussed earlier. Okay. So positive means it come out lah. Leak also positive because it's come out from the control surface. If you have a system pump in liquid, then you have a negative there. But in this case, we don't have anything pump in. Only liquid come out from this device. So you have positive sign there. Okay, we continue using the software, using the equation. So because of this one, the whole thing is equal to 0. We can move our equation to one side, right? Now the non-value will move to one side, and the integrate will just stay put there, right? All right. So we have okay. Now because of m dot means m, you have dm dt, dm dt here. So when we move outside, we can take out the dt term. We only have this one. This one is our m. This is m at section 1. M at section referring to m dot 2, which is here. This is leak. This is referred to a leak. And this one is the needle. All right, now A1 is same with our plunger area. So we continue calculate what we know, right? So just put back the equation just now. So in this case, why we cancel out the term for the needle here? Because it's very, very small, right? Rho, del, volume by the needle, and the change of time. This one is considered very, very small. So we can cancel out, right? And what else? Okay, so the equation will come to this way. So del over del T at a control volume component will be equal to rho A1 del L over del T. So del L over del T actually is our velocity of our plunger, because it's a change of length here. It's actually our velocity here. However, the length was decreasing as we push in. The length is decreasing here. The L is decreasing if we push this length. So in normal case, our velocity Vp will have a negative sign there. So Vp equal to negative change of length by the time. So be careful on the negative sign here. We put the negative because as our velocity of our plunger build up, the length will be decreasing. Right. So we pull this equation in here. All right. We pull in our equation here. Pull in here. All right. So we have negative rho A1 VP plus m dot 2 plus m lick. Just now we, at the left hand corner here, is actually all these things. Then we substitute back here. So again, in this case, with a negative sign in front. So negative rho AV1 VP plus m dot 2 plus m dot lick. M dot 2 equal to m dot equal to rho AV. Also Q2, because Q2 is given. Again, be careful on the unit, because the unit here is cm cube over minute. All right, be careful on the unit. Lick, m dot lick equal to rho AB also. However, the lick is given is equal to 0.1 Q2. So you can link the lick into in the term of Q2 here. So you put these two information inside the big equation just now. So m dot 2 become rho Q2. M dot lick become rho times 0.1 Q2. So here you have 1, 2, 3, 1, 2, 3, 4. Four unknown here. Of course, again, you see the rho here. And because of the water or the solution that we use, we assume that is incompressible. So again, we take out the rho here. All right. We combine these two, rearrange. All right, so you have 1.1 Q2 here, take out the rho. At the end, your VP, your plunger velocity equal to 1.1 Q2 divided by A1. Right, substitute all the known value. Be careful on the unit SI. Right, you change to everything there. So straight away I give you the expected answer. So this one is 660 mm per minute. So this is a raw answer. After you do your calculation, you get 660 mm per minute. So in exam, you will be more specific, ask you to put in a certain unit. For example, meter per second or something. Right. So this example just show you the steps that we expect you to do when there's a moving control volume. In this case, there's a springer. So for engineering case, maybe it's a piston. When you have a hydraulic system, you push something in to lift something up. Then you can use this kind of approach also. In this case, we apply on the string system. But the same approach can be used to solve hydraulic system. Okay. We have done for question 1.5. Any question? We have solved for question 15 already. This is how we apply the Reynolds theorem in this case, right? Yeah, and also although there's no statement saying that incompressible is assumed, you can assume that it's compressible because that is how the Springer or hydraulic system works. We assume that the liquid that we use is incompressible. Any question before we move to the next tutorial question? Good, huh? Okay, good. We move to 1.6 and then after we solve this one, we go for a short break. We solve this one first and then we move to the next one. Okay, question 1.6, we use the same example as question 7 for this right, for this tutorial. We use it exactly the same, we change something else. Right, we change something else from question 7. All right, again, it's an application of knowledge. We want to test whether you know to use which is the suitable equation to solve a certain problems. So in this case, again, we have the same size of the trench or the channel here. We have the same size, 3 mm, 3 meter long, 1.5 wide, 2.5. Is it the same? Let me check. Yeah, it's the same dimension. So as a near or being near to intersection, carbon dioxide from the engine enter the trench at the same rate, 3 meter cube per minute. All right. Assume there's no mixing. All right. Now we need to solve this problem using a deforming control volume that includes only the carbon dioxide accumulating in the trench. We only focus on CO2 inside the trench. So the first one, estimate the time rate change of the depth or del H over del T in meter per minute at any instant. So we need to use the deforming control volume Reynolds theorem to solve this question. All right. So again, you just drop out the same setting, the same control volume that you have. So your CO2 enter from the top of the control volume, height 2.5 with the H there. We want to find del H over del T later on. And then we have a base of 3 times 1.5 meter. Okay, I'll give you some time to draft out. Just a simple shape, cube with a control volume. All right. Always label your diagram with control volume. All right. So for chapter 2 question or your coming test 1, you will cover this chapter. So when you solve problems, your diagram also will help you to solve the question. Okay, so now we need to use the deforming control volume. Again, call out the Reynolds transport theorem that we covered in question 14. All right. So the change of mass in the system equal to del over del T in the control volume times whatever change in the control surface. In this case, again, we look at W rather than the U. And we look at only on the CO2 component. CO2 component. So our equation further reduce. Del over del T integrate our CO2 control volume density times the change of volume plus integration of your control surface density times the relative velocity W dot the vector reference to the control surface dA equal 0. Okay, we make some small calculation for the first section first. We look at this section first on the right hand side here. So del over del T for your CO2 equal to del over del T, rho still the same, rho H, your velocity H times the base 3 times 1.5, because this is what you know, only change the H here. All right. So you can simplify the equation into del over del H. You pull your H out because H is the one that is changing. Rho is still the same. Rho is a constant value for whatever medium that you use. So your equation reduced to del H or over del T times 4.5 rho. This one rho here refer to the CO2. Okay, we put the equation back into the earlier one. So the first term become del H over del T times 4.5 rho. And then your second portion is still the same, you copy. Right, so far in the exam, you'll get 1 mark for this one. This calculation, maybe 1 to 2 marks. Up to here, we see how we give you marks. Right? So we have this equation. Again, we look at the second component here again, on the right-hand corner. So integration of your control surface component here, you have your, this one is actually is the m dot. So again, recall what is m dot is rho AV. So we have two things happening here. One is your CO2 enter, and then your CO2 increase here, right? So again, here is the velocity, relative velocity, and both is the entering, into the control volume. All right, I explain why we can assume this one negative, this one negative. So this one enter is very direct, so direct is negative. What happened to the bottom one? So your CO2 accumulate from the bottom, right? Accumulate from the bottom, become second layer, and then so on. So your CO2 actually accumulate and enter into the control volume from outside. So that's why you get a negative sign here. Okay, that's why you get a negative sign for second component. Yeah, I explained already. So this case, we only look at CO2, and because of the deforming control volume, we have two components here. One is from outside, one is from bottom accumulate. So at the end, we can simplify our equation into second term of our equation here, integration of our control surface rho W dot n hat dA equal to negative rho A CO2. This one you times because we carry out the negative sign outside already. So we have V CO2 plus del H over del T. Here we carry forward into our equation to solve it. further. Right, we carry this one in. All right, make sure you understand why there is a negative there. Make sure you understand. Right, we want to find the dH over dt. You simplify the equation, move whatever not relevant to the right. All right, because both have del H, so you do the mathematics arrangement. At the end, you arrive at this form. So del H over del T equal to A V of the CO2 divided by 45 minus A CO2. After that, you substitute all the known value. You can find what is del H over del T. Right, here to here is just a mathematical arrangement. Again, the row we take out already. The row here is the same, so when we factor out, we can take out the row in this equation. So that's why we arrive at the equation without the row. So for control volume question, most of the time we do not need the row value, because of course when you solve the question, we still need you to show us the steps. Okay, can we move on? Anyone still copying or still need some time to copy the answer? Let me check the attendance. Okay, Brian is here. Bila is here. Bila, again, you need to log in with your Nilai account. Okay, I go to okay, attendance. Brian and Bila again. You late for class.
No, sir. 7 minutes late.
Which one? Who is saying? Who is speaking? Who is speaking? Brian, is it?
Yeah.
Brian, what time you log in?
Probably 7 minutes late.
7 minutes late. Okay. Okay, this time Brian, right? Bila, any explanation? Apa late, Okay. Continue. So, yeah. So AV is the Q. Someone text. Okay. Right. So AV is your Q. So you just substitute the answer. All right. Because this is the division problems here. Q divided by 4.5 minus A CO2. So we can only solve something that our area for CO2 is much less than 4.5. If not, our equation will become infinity question. Something divided by 0, then it's an undefined question. All right, so in this case, we assume that our area of CO2 is very, very small compared to 4.5. So we estimate, this is the estimation or simplification, these steps here. Simplification because we have a statement saying that our area of our CO2 here is much, much smaller than 4.5. Then you can able to proceed with the calculation. You take Q is given 3. In the question was given 3 meter cube per minute divided by 45. So 45 is not 45. 4.5 is meter square. Then we have something with a unit meter per second. So in this case, the reference answer is 0.667 meter per second. All right, for this module, maximum 3 decimal. This is just to show you the reference answer. All right. Okay, we have complete the first section using the conservation of mass. Yeah, I think we have a short break. We continue at 4 o'clock. We come back after half an hour. All right. Let me stop the recording.